You can see that it often achieves lower asymptotic performance in the sense that when you run PPO, you'll almost always get extremely high performance, whereas with SCC, it'll get there quicker, but kind of plateau a bit lower. And because you're storing replay buffers, you often need to maintain a lot of memory, right? And so on policy methods will have huge batch sizes, but they throw away the data after. So you need lots of RAM, but replay buffers need to maintain like millions of just like samples in memory, and that can be hard for like images and these kinds. And so those are some trade-offs. If you're using robots in the real world, I would say use these kinds of robots. Do you use off-policy RL methods? If you're using robots in SIM or doing SIM to real transfer, I'd say use on-policy methods, right? So if you're trying to like figure out which RL method to use PPO, unless you're trying to do robots in the real world, in which case use this, right? Or SAC plus. And for those of you who are trying to do practical things, stable baselines is a great implementation to start. Okay. So that's off-policy RL. And so what we're going to talk about today is we're going to start thinking about model-based reinforcement learning and what it means. So we're going to design the basic anatomy of a model-based RL algorithm. We're going to start with the stupidest version, which is just random shooting. We're then going to add in a slightly fancier sampling method, MPPI. We're then going to incorporate uncertainty into our models. We're then going to try and do policy optimization. And then finally, we're going to do it with images, right? Oh, okay. But the point here is that there's like, if you look at the history of model-based RL, at least in the last 10 years, we kind of started with the simplest thing, and then it has a nice story of incremental improvements where we improve the sampling method, we improve the model, we improve policy optimization, we let it work with this. And so they form a nice sequence of methods. Okay, makes sense? Any questions? Burning concerns? No? Okay, good. How many of you have heard of model-based RL before? Okay, great. Maybe we can skip the first part. But the general landscape we've talked about gradient descent, which is policy gradient. We've talked about dynamic programming through actor, critic, and Q-learning methods. Right? And what we're going to think about today is model-based optimization. So we're going to think about model-based optimization as a technique for still optimizing the same objective. So the objective is still maximizing the sum of expected rewards or expected sum of rewards. And we're going to think about, rather than doing direct gradient descent or dynamic programming on this objective, how do we construct a surrogate model, then optimize that surrogate model? Okay, so instead of trying to directly optimize the objective right over there, what we're going to do instead is we're going to say we're going to get a bunch of transitions from the environment, right? So the assumption we're going to make is you can sample from the environment, but you don't know the functional form of the environment. You can just get samples. And so what we're going to try and do is construct an approximation to the transition dynamics of your environment, right? Construct an approximation that tells you how does S and A transition to some S prime. And then we know the functional form of our approximation, so we can then use it for policy learning and policy optimization. And so the key idea in model-based RL is to learn a surrogate model. When I say surrogate model, I just mean you only have samples from here. You're going to try and take a model to those samples, and then you're going to use that as your approximation to the true model, right? So you don't have access to the true model. You only have access to samples. You're going to fit it, and then you're going to try and use that as your like world model, right? So this is often called certainty equivalence, right? But the point is that you're going to try and fit a surrogate model, pretend that that's the real world, and then do policy optimization in that state model. And so the whole premise of model-based RL is how do we learn this surrogate model accurately enough? And then how do we do reward maximization against this surrogate model? Okay. So I guess a natural question to ask is this even difficult? Like we spent the last 5 weeks doing the second part, right? And we can just do the first part with whatever, supervised learning or something? Like why is this hard?
Because like stochasticity in the environment, like hard to capture that without a lot.
Right. Stochasticity, and if you don't have enough samples, your model is going to have like holes in it, and you're going to have like lots of propagating errors. Right? And that's what's going to make model-based RL hard. Okay, but the intuition here is that you often try to learn how the world works first, and then plan in that model. Right? So as opposed to model free RL, which is saying, screw how the world works, I just want to get reward. In model-based RL, you're going to try to learn an approximation of the model, and then try to like plan in this. Right? Where planning is just trying to find a series of actions that maximize reward. Yes. Okay. Why should we do this? Seems strange. We like PPO solves all problems, right? So why should we do this?
Yes, you are more sample efficient.
Is more sample efficient? Yeah, absolutely. The hope is that it's more sample efficient. And I think in certain cases you can show that it's more sample efficient. So that's one for sure. Might have that somewhere in here. There, but I don't want to reveal the other one. What are the other ones? What are other reasons that models might be useful for? Yeah.
Model free cannot work if I add some features to robots. So it is model based more generalized.
If you add some features to the robot?
So because like the concept model free is that not the same exact model.
Yeah. Mm-hmm. Yeah. I think maybe one way to restate what you're saying is that model-based RL is learning a model of the transition dynamics, but not of the reward is separate. So you can swap out new rewards, and you should be able to use the same model with many new rewards. And so it gives you a benefit in transfer to new problems, right? And so it lets you, if you can model the dynamics well, then you can swap out lots of different problems. So just swapping out the reward function. So you can reuse all the same data for many different rewards. If you look at like policies, they're specific to a particular reward. Like 5-star is 5-star for a reward, not for a different reward. Or QPI is QPI for a particular art, not for a different art, right? And so the nice part about model-based RL is the model irrespective of the reward. And so you can swap out new tasks in principle. And so it gives you the ability to be adaptive. Secondly, often this is a paper from one of my friends, Anusha, that is model-based RL, that is model-free RL. It's even hard to see model-based RL, but it gets to optimal performance significantly more quickly. This is not always true, and I think this was in 2018 or 19, different now, but it is often more sample efficient than model-free RL. And lastly, it's kind of simple, right? It's just like you learn a model with supervised learning. You don't have to deal with all of this like fixed point iteration, the dynamics of learning, and all of the pain of dynamic programming. You just have to do supervised learning. Okay? And so at least these are the reasons I think model-based RL is interesting, and my own group has been investigating a lot of model-based RL in the last 2 years. I think it's cool. Yeah.
Sorry, when you say just do supervised learning, a little confused because I feel like teaching towards like behavior coding, you like that's a while back.
Yes. That's a good.
Is there somehow model based?
No, that's a question. So when I'm saying supervised learning, so in behavior cloning, you're trying to learn a mapping from S to A star. Here, what we're trying to do is we're trying to learn a mapping of the dynamics, so S and A to S. And so it's like a different supervised learning problem. But what we'll see is that a lot of the issues that happen in behavior coding also happen in. But like as an objective to optimize at least just to learn the model, it's just supervised learning. When you use the model, a lot of those issues show up. So yeah, maybe that's a bit of a simplification in the sense that it is simple to learn, but difficult. Okay, does that make sense? Does everyone believe we should at least study model-based RL and then decide whether it's garbage or not? Yeah, okay, good. So let's, oh yeah, and last point is that it's naturally off policy, right? Because you're learning a dynamic, you're saying, I'm going to learn a mapping from states and actions to next states. Those states and actions can come from any policy, right? So it's like a naturally off policy method, whereas things like policy gradient are forcibly on policy, where the dynamics of the world don't depend on what policy you run, right? Like S and A transition to S prime, it's a fundamental nature of the environment. It's not dependent on what policy you run. That's with some caveats, like which states you learn your model on depend on the policy, but the mapping from S and A to S prime is not a policy dependent entity, right? So if I like learn, if I consider my definition of MDP from the first lecture, right? If I consider this mapping, P of S prime given SA, we're going to try and approximate it using some P hat of S prime given SA. This works no matter what policy you stick in, right? Like this is a fundamental nature of how the world transitions. This is physics of the world, right? And physics of the world doesn't depend on what policy you run. Okay, so the policy you run will determine this thing, but the rule to transition remains the same, right? And so model-based RL is naturally off policy. And so it has the advantages that we want, but it's going to come with some cons. We'll talk about. Okay, everyone with me so far? Good. You say kind of?
How it's actually policy versus.
Okay, let's delve into it a little bit, right? So like the dynamics of the, well, I guess maybe let me get to exactly what we learn, and then we'll dissect it. Okay, and I heard from my friend Anusha, who's like an absolute expert in this space. These are some of the results from her internship at Google, and she was trying to get this robot to like rotate these balls in hand. And this is with less than 2 hours of training on a like 24 degree of freedom robot hands. No simulation, no nothing, just like learning the real world. Which is like, I think even now. And so, yeah, I think it can work extremely well if done right. Okay, so this is going to be using like basically some of the methods we talk about today. So it's not that far off to implement it, right? So, all right, there's some connections to cognitive science for those of you who are interested. Like, yeah, Nate has like a bunch of work on how like prediction is a big part of like learning in the brain. Maybe you could tell us more about it, but like in general, I think there's like lots of debate on whether we do like model-free things like PD error and reward error prediction, or things like world model prediction. Almost certainly we don't do next frame pixel prediction, but it's still quite interesting to study. Okay, so let's look at the problem statement, and then we'll try to get the concrete. So the problem statement is we want to learn an approximate model of the world. And so let's say we have we're going to assume that we have some sort of data set B, which is drawn from the environment. And we're going to try and construct a loss function L so that we can learn some surrogate model B theta hat. In our case, which maps from S and A to S prime, right? So the model is going to take in S and A, it's going to produce an S prime, right? So if your states are images, then it's going to produce, if your states are like positions of the object and the arm, it's going to produce those, right? And so essentially what this is saying is that you want to find, we're going to choose different loss functions, but it's trying to say, given some data of S, A, S prime, try to fit a mapping with maximum likelihood of S prime given SA, right? And different objectives will lead to like slightly different, whatever, learning problems here, but essentially we're trying to find an approximate model of the world. And so just like behavior cloning, we're going to do supervised learning together. And the second part is once you have your approximate models, you're going to pretend it's the real world. If you're going to pretend it's the real world, you want to do reward maximization. But notice that rather than optimizing under P, you're going to be optimizing under P. Right? And so you're going to learn, this data is going to come from P. You're going to learn at P hat. And then you're going to do policy optimization under P hat. Right? And so this is what you'll often call planning. And that's often what you call modeling. Does that make sense? Okay, good. So the general anatomy, like often with different model-based algorithms, they're just going to choose different objectives here L and different optimization algorithms and have different planning algorithms to deal with the fact that this B hat is a. Okay. So the question becomes, how do we actually instantiate the model learning objectives L, and how do we actually do planning for finding pi, right? One important thing to remember is that often in model-based RL, this is going to be done at test time, which means that like I'm going to have the model, I'm going to carry the model around with me to test time, and then I'm going to do planning at test time. Like in reinforcement learning, model-free reinforcement learning, we did policy optimization at training time. We got a policy, and at test time, you just run the policy, right? You just like get in states, you put it through your policy, you get actions, you run your actions, you repeat, right? You're not doing any test time optimization of it. Whereas in model-based RLs, often what you'll do is you'll run this test time optimization at test time, or you run this optimization at test time. You'll keep your model with you, but you'll run the optimization to find like the best set of actions to run in the environment at test time. Right, so it's like I learned this from a bunch of data, I get deployed in a new scenario and keep my model, and then to act, I run a planning procedure at test time. And the nice part about doing that is that you don't have to learn how to do everything. You just need to learn how to do that one particular scenario that you're doing, right? And so while model-free RL pushes a lot of the computation to training time, model-based RL lets you do that at test, right? And the thing that makes it work is that in model-free RL, you need to learn how to go here and here and here and here and here. At model-based RL time, you're like here, someone tells you to go here. You don't have to learn how to do everything. You just need to use your model to find the actions to do a single trajectory. And so you kind of don't care about getting a generalizable model because you're doing it at test time, or generalizable policy because you're doing it at test time, right? And so there's some trade-offs there. It doesn't have to be this way, as in you can have methods that you use the model at training time too. But a nice advantage of having the model is that you can do it at this time, right? And so for those of you who do like control Z things, there's kind of like you can run MPC and so on at test time. You don't have to run it at training. Okay. Sorry, give me 1 sec. Okay. So, okay, does the problem setting make sense? Right? So the problem setting is we collect some data. Data is going to be used to learn a model. Model will be used for plan. Model learning is trying to like do maximum likelihood given collected data. Planning is trying to find highest reward policies under your approximate model. Yeah.
This is a question that like we're have something like complex world and then we're like making a simpler model of it and then plugging it into the plan. I mean, to me, it seems like it would perform worse than just plugging like the version of it. What is the
Well, you're often going to the nice part about having a generative model, like something that is generate data, is that you can go beyond the experience that you have, right? And so you had some amount of real world data and off policy RL or policy can use it directly to get your policy. With the model, the hope is that you can like generate more data that's useful to do policy optimization because you've learned a generative model of how transitions happen in the code, right? And so the premise of model-based RL working is that something has to generalize.
are we assuming we don't have access to like the world to sample from it?
Exactly. So you assume you don't have access to the world, you just have samples from it. And then you try to learn something that can generalize to your setting without taking more samples from it.
Let's say we have access to the world, but this still
Then you don't.
yeah.
Yeah. Yeah. If you had access, so like for instance, you're doing things in a simulator, never do model-based RL in simulator. The only reason to do model-based RL in simulators is basically to construct like a differentiable surrogate. So then let's say you had a simulator, but it's black box. You can't take gradients, etc. The reason to do it in a simulator is so that you can take gradients to the model and to potentially smoothen the optimization landscape. Cool. Any other questions before we keep going? Okay, good. So what we're not going to cover today is ILQG and ILQR. Dieter's class covers it well. You should go look at his lectures. We're not going to cover model-based RL with Gaussian processes and non-parametrics. They also work well in low-dimensional action spaces and state spaces. A reference I'd recommend is Pilko. Pilko is a really good paper on model-based RL. And we're not going to cover like techniques for nonlinear trade-off. We're going to stick to mostly learned models and and things like that. I recommend Russ Sedgwick's like under-actuated robotics notes. They're very good for nonlinear trajectory optimization. Yes. So also watch Byron's lectures. I think they do a good job. Okay, what we will cover today is we're going to think about using neural networks as our model class, right? So we're going to say, we're going to get rid of it. As Adrian was saying, we want to approximate our model with some sort of simpler approximation. Our simpler approximation is going to be a neural net. And so it's not that simple, but it has some generalization properties. And we're going to try and study both model learning and planning in that context. Using a neural net is going to introduce some unique challenges because neural nets have like overconfidence issues and they extrapolate in weird ways. And so that's going to make our planning a bit harder. And the nice part about this is that we can then try to get results that look like this. This is using, both of these are using MPPI. This is some results from Byron's group at Georgia Tech. And the other ones are from Google, right? And so both of these use model-based RL with just small amounts of available data. So we'll try and enable these things. Okay. So before we get into the methods, a few assumptions we're going to make, right? The first assumption is we can only sample from the dynamics. We don't have access to the world. We have access to samples. We're not going to assume access to resets, right? We're not going to assume access to like arbitrary resets. We're going to say that the environment can reset to a particular spot, but it can't reset arbitrarily. And so just like the normal episodic setting in model pre-RL. And we're going to assume that the reward function is known, which means that like there's some analytical function that's given to you that you can take in a state and evaluate its reward. Okay? So in model 3RL, so far we were assuming that you sample in the environment and then the reward function appears magically, right? And here what we're going to assume is that rather than doing that, you have some sort of function that is able to take in a state or an approximate state and tell you how good that is. Right? And so the reason to do that is because you're going to do planning by like hallucinating states. And so you need to know how good your hallucinated states are, right? And so we're going to assume only samples, which means we need to learn a model. And we're going to assume that the reward function is known so that you can do planning and hallucination, right? So if you have a fake model of the world, you need to know how good things are in that fake model so you know the reward function. You can also do things to learn the reward function, but we're not going to cover that. Yes? Okay, good. And we'll cover that next week. We'll try to cover how to get reward functions and reward inference and inverse RLs. Okay, so a template for model-based RLs is something that looks like this. We start by collecting some data. Then you go and learn a model, right? Then you do planning. You get some sort of policy, you execute in the world, you get more data, use that extra data to learn more of your model and repeat, right? And so you're just going to go in this loop of data collection, model learning, planning, and like how frequently you do each of these can change with different algorithms, but almost all of them have this tough procedure. And we're like this part is like standards, but we're gonna try and instantiate model learning and planning. Okay, so that's kind of the anatomy of a model-based RL algorithm, right? Like how the general structure looks. Let's try to get into some details. So what is the simplest possible thing we can do for modelers? We have some data in the world. We want to learn an approximate model of the environment. What is the simplest thing? Maximum likelihood. That's it. Okay. And so the simple thing we do is maximum likelihood. And now you have, an approximate model P theta hat, which tells you if you're at state S, you take action A, you get to some state S prime, right? What's the simplest thing you can do for planning? You just want to find, you're at a state, have a model, you want to find which action to take in the world. That's what planning is. What's the simplest thing? Brute force, that's it. So you just do random search, right? And so you're going to say, like, take your model in, just do a bunch of random shit, pick the best random stuff. And that's all that like random search is going to be, right? And so the simplest version of this algorithm is you're going to start by doing maximum likelihood to fit a one-step model. So you're going to say, I'm going to sample S, A, and S prime from my environment. You're just going to maximize the likelihood of S prime given S and A. You learn the parameters of your policy or your model data, right? And once you have those, then you can try and do like planning things downstream, right? And so This is just a standard supervised learning procedure, just like you did in behavior coding, right? You're gonna collect some data, you're gonna do supervised learning, you're gonna learn. Now, what is the choice of p theta hat that we should use? Right, so we talked about this a bunch in imitation learning, right? It's kind of the same problem. So what is the, yeah, what should we use as p theta hat? Gaussian, right? So the Gaussian is the simplest possible thing to do. And the Gaussian is going to be just like mean squared error, right? So if you said p theta had to be the Gaussian, with fixed variance, this is going to be the L2 distance or mean squared error, right? And this is great if your environment is close to deterministic. Many environments are close to deterministic, and if you learn this, it's great. It gives you something reasonable, as in it's a unimodal distribution of what the next state is going to be, right? So it's like saying that if I was at this state S, I take action A, it's like probably going to go like somewhere here, right? But in stochastic environments, like there's one where you often have like, you like drop a ball and you have like a bunch of these, like, you guys seen these environments where you drop a ball and it bounce around? Right, the pegs, yeah. In those environments, it's often quite stochastic, right? Like, things that seem like they shouldn't change the behavior goes left or right randomly. So in those environments, what should I use? Like, I wanna deal with stochastic environments, so things where one S and A can go to a different S prime. Right? And so in those settings, what should I use? Autoregressive model, yeah, that's great. I had energy-based models in there, but you can use arbitrary models, right? So you can say, you just want to use, you can think of this as just a generative modeling problem, right? It's a conditional generative modeling problem. You're trying to take an S and A and learn a distribution over S prime. You can use autoregressive models, you can use energy-based models, you can use diffusion models. They're all going to let you represent stochastic dynamics, right? But in practice, often, like lots of environments are kind of deterministic, so Gaussians work surprisingly well, right? And so, at least in robotics, I don't know about other. But yeah, so you can just think of like this recipe allowing you to instantiate a bunch of different algorithms. Like one paper you also read is called Diffuser from Michael Janner, which is just saying replace that p theta hat by a diffusion model, and like papers like that kind of have the same idea. Okay, so all we're going to do for model learning is maximum likelihood. Different p theta hats will lead to different algorithms, right? And the trade-off you want to make is that sometimes if you have more expressive models, you can have overfitting, and these models will get worse in sequence. And sometimes that's why Gaussians and simple models are good for model-based setup. Okay, so that is our simple algorithm for model learning. What's our simple algorithm for planning? We talked about just doing random search, right? So you can construct a simple problem where you say you're just trying to find a series of actions, right? Which when you execute in the world will give you like the highest possible reward or discounted sum of rewards, right? And you can solve this problem lots of different ways. If it's convex, you can solve it with a convex solver. If it's black box, you can just solve it with random search, right? And so all we're going to do with random search is we're just going to sample a bunch of random series of actions, right? Which means that you're just going to sample like A naught to AT randomly from a uniform distribution or a Gaussian or something. And then you're just going to evaluate each sequence of actions for the best possible one. And then you're just going to execute the best possible one, right? And so essentially you just like try a bunch of random stuff and then see which one did the best and then like execute the best one. Okay? Now that's just random search. Policy grade is not that different than random search, but essentially it's just trying random stuff and choosing the best one. Why might that not be?
Hard and high.
Perfect. Yeah, it's hard in high dimensional spaces. And the other problem is that it's open loop, right? So it's like if you like execute these actions open loop, let's say something happened that you didn't expect, you cannot replan, right? And so you like drift off the path and you're just off the path and you've crashed your car, right? And so the issues here is that it's hard to search in high dimensions and you're executing open, An open loop is not going to deal with model errors. So how do we fix it? How do we fix part of it? Like, there's two problems. One is hard to search in high-dimensional spaces. And second is that actions are taken open. How do we fix it? Yeah. Discretize? Yeah, that's a reasonable suggestion. It's just really hard to do in higher dimensions. Because you're like the number of discrete bins you have is going to and it's also hard to know like how to discretize without losing like policy performance. Other ideas.
Like, try to use this formula to estimate values. The states that
Right.
each of the states.
That's right. Exactly. Right. So the easiest thing that we can do is like essentially do like replan, right? Which means that like if you have an open loop controller, it's going to diverge even with little bits of noise or little bits of deviation, and it's going to be worse with the learned model. Right? So in control, often you have some stochasticity that causes instability. Here you have a learned model, it's going to do crazy shit. And so what you're going to do instead is that you're going to like choose the best set of things. You're going to execute some actions in the real world. So you did planning, and you executed some set of actions, and then you replanned from your new initial state, right? And so let's say this was your first thing. If you did open loop, you're going to like fall off the cliff and like, no longer, this is kind of the same issue as behavior cloning, right? When you make a little mistake, you make a bigger mistake, make a bigger mistake, and so on. Or similar issue. Instead, what we're going to do is we're going to do replanning, right? So we found our best possible thing. We're going to execute some actions. It didn't go exactly the way we wanted, but we'll do more replanning, and then we'll execute the next one, and we'll do more replanning, and then you kind of get something that like at least has feedback, right? So like a lot of you are probably familiar with this, but this is like non-predictive control or receding horizon control, right? Just saying that you're going to do random shooting. It doesn't have to be random shooting, but here we're saying we'll do random shooting, but we'll do it repeatedly and just replan frequently, so that we like can account for issues in our errors in our model, right? And so a lot of the times, just replanning can deal with like little inaccuracies in the model. And so the first idea we're going to apply is we did simple model learning. The model learning might be imperfect, but you might not go the way you thought you were going to go, or your search might be imperfect because we did random search. And so if you do replanning, at least you can account for deviation.
Why do we go over all the actions?
It's a great question. Yeah. So Ethan's question is when we search through here, why do we go through all of the actions in the horizon, right? Rather than just like one. Now, the tricky part with just doing one is that you're in a sequential decision-making problem, right? So you can't just be greedy. You have to account for like the long-term effects of your actions. And so you have to like plan over the entire horizon, or like some horizon, because you have to account for the effect of your actions long-term. So something that people do to make this easier is that when you're doing replanning can let you shorten the horizon of search. Right? So because you're doing replanning, you're saying, I don't need to plan that far in the future because I know I'm going to replan later in time. And so you can like go from P to like a smaller number. The other thing people do is they'll add like a terminal cost function here. And so that lets you like bring the horizon down because the terminal cost function accounts for like what's going to happen in the future. And so the answer to your question is because of the sequential problem and like states and actions affect next states and actions. So you have to account for a horizon. You can't be greedy, but there are ways to shorten it with replanning and like terminal values. Yeah. Okay. So we did the simple MPC thing, right? MPC is just saying do random shooting, but do it repeatedly, right? And so you start by planning with random shooting, executing the first action and the first few actions, reaching some new state, repeating, right? That's it. That's all that replanning. But it's super powerful in that it lets you get away with a worse model and lets you get away with worse planning, right? Because it says that like, as long as you're kind of going in the same direction, you like will be able to replan. It's not always true, as in you might have catastrophic failures, but if your model is not terrible, then replanning lets you get away with it. Yes, believable? Okay, so putting these pieces together, what is our first version of the algorithm? You collect some data from your planner, you do supervised learning on all your data thus far. Then you do planning with random shooting plus model predictive control and replan. And then you go back, collect some more data, and then repeat, right? And so you've collected data, you're adding it to your replay buffer and doing supervised learning. Then you're doing planning by just running random shooting. Like the way you're going to do it in practice in your homework is you sample a bunch of random actions, run them forward through your model, take the best one, evaluate the first step, execute, repeat, right? That gives you your new data. This is kind of like a policy. You can think of this as like an implicit policy, right? Because you're saying that like this whole procedure, right? This whole procedure is something, let's call it implicit policy. It's taking in a state and it's giving you an action to execute, right? And so the thing is basically a policy. Saying, taking a state, do this random shooting procedure, whatever, find the best one, take the best action. That's like one step of your policy, execute and repeat, right? And so this is not that different than a policy, it's just implicit in the model. It's not like a neural net that's going to save the action. You're using the model to do planning at every step, right? And so you can think of this as this planning thing as the same type as a policy, right? And then you like go back and do more data collection, and then you do. So to answer Fadl's question from before, like why is this naturally off policy? It's because when you're doing maximum likelihood, you can just like keep feeding data from whatever, right? It's saying that like S and A to S prime is like a stationary distribution. It's inherent to the environment. It doesn't really depend on the policy. Like you can have many different policies executing in the same environment, and they're all governed by the physics that takes you from S and A to S prime, right? And so essentially this data set can come from anything, right? And the caveat here is that if this data is very far from optimal, you won't be able to find optimal actions, right? But you can still be off policy. So it's still subject to the same coverage assumptions that we talked about last time, right? But it can be off policy. Yes. So the point is that this algorithm is naturally off policy because the dynamics are consistent no matter what policy you have. Like that's how the world works. And the policy is implicit. The model completely defines the policy. Okay? The planning algorithm plus the model define the policy, and so it's an off policy pattern. Yeah, exactly. You can swap this out for whatever you want, right? Whereas with a neural net policy, you just can't do that, right? And you have to do all this like fancy sauce to do. Okay, we're at 12:17. Let's take 3 minutes and we'll go through the next step.
Okay. It's like the in general, I understand that yeah, like you start seriously considering working on it. Because like you can do it now, obviously. I just don't know what to expect.
So for your project, you have to go as a paid. Yeah. I think realistically, what you earn the first week of paid.
Oh, no, right.
Depends how compelling you want to make it. Like they don't apply it across data. I say like it takes us 2 weeks to get the project to work, and then it'll take like a week or 2 weeks.
Yeah.
So I would say like start now if you want that you could make.
My idea was to start off with point made to implement like some kind of, I don't know, some IQ learning, like it's like very, very simple baseline. And then implement like this, the paper that like my thing is supposed to build off of, and then hopefully, you know, add it on. That's right.
That's perfect. So it's a start now. It's always better to start.
Yeah.
I was gonna ask for a check-in maybe next week.
Okay.
I'm a little stuck, so I'm learning all from all this. Yes. So why this all that's being yeah, that's what we want. So what you want is something that can represent the world so that you know how to act in it.
But like that's like more than like in a simulator, like it's more than what it would be, right? Like,
Yeah, so simulator is the same type as the model.
Yeah.
But the goal of learning a model, like I guess the goal of most of what we're doing is so that we know how to act. And so like the goal here is not accurate simulation as much as it is accurate like policy inference. Like, I really want to figure out how to act in the world, and the model is just a tool to allow you to effectively. Right? And so like you can think of the reason you want to learn a model first is so that for new tasks you can simulate one possible outcome that makes sense. So that you can stick in different controls, find the best one, convert it into the best.
I see.
And whereas for, let's say you're doing model 3 you can solve it for a single task, and for new tasks, you have to do it. Right? And so building a model that you like, the goal is not better simulation, the goal is better.
I see. So then like, why would it be like, what if we had like a simulation? It's like, it seems like being able to go backwards and invert it and like find out the best action, like that would still be useful in simulation.
That would be, but it's also hard to construct a simulation. Like if you're using like a physics simulation, you include it here. Yeah, it's like hard to construct a simulation that's accurate with the world, right? Right, so like if I'm like trying to do model-based RL here, I have to like estimate where this is and the physical properties and all of these things. And so it's hard to construct a simulator of the current world. Where what model-based RL will do is use like data to do that, like inference, right? And so it's essentially trying to construct a simulator, it's trying to construct an end-to-end differential without physics.
That makes sense. So then like, what's the idea about like planning and replanning? So like, let's say take one step.
Yeah.
You went to DD. So like, what does, are we replanning from that like?
From that new state that you're in.
I see, okay.
Right, so you're like, if we're like looking at this thing, right? You started here, and then you made a mistake and you ended up somewhere else. And then you start the planning process from there. So you're gonna like sample a bunch of random trajectories from there, and plan from there. But you're aware of your and so it lets you like, I think those loop where the open loop would basically execute the action that was supposed to be executed here, it'll execute it here, even though it's wrong.
I see. So, well, people will like do like predictable actions.
Yeah, exactly.
Okay.
Exactly.
And this one's going to do that.
This one's gonna keep replanning there, right? So it's gonna like correct for mistakes up to the limit of your model and your planner, right?
Is the data still just like trajectories from?
Yeah. The data still activate as well. Because we know the reward function, you don't need the reward function, you just need sequential. I see.
And then I also have a question about Q learning versus like multi-value work. I don't really understand like why, I understand like why Q learning can be awful. But like, why can't we do the same with like evaluation, like learning that, like getting like a state in action and say, okay, let's just have our target always be like this state, this action, and we like are, we know like that S prime, then like, why don't we just do that?
So, how about we chat after class? Let me
Okay.
get into this on the whiteboard. I just want to make sure we get to model-based RL, but find me after class. We'll go there. All right, let's keep going. So does it work? This
Here, the swimmer
this scheme, which seems so naive, does seem to kind of work. This is with a neural network model for these like little swimmer tasks, which are all the rage in 2017 and 18. But it's trying to follow these waveforms, and it's just like use data to learn a model and then do like random shooting plus replanning. Yeah, I think it's like pretty surprising with a neural network model. And then it's a little hard to see, but like there's a little cockroach here that's like following some set of waveforms, which are like laid out over here. And this is like an extremely hard to model system. It's like this cockroach made out of plastic and changes all the time, and it's bendy, and it's like not easy to build an accurate model that you can plan with. But they just learned this model from like 20 to 30 minutes of data, right? Which I think is pretty compelling. So yeah, it does kind of work, right? But there's some caveats that it doesn't work as well as some of the methods we discussed in the last 5 weeks of class, right? And so if you look at the performance, model-based RL is shown here at the start, right? And then model-free RL is shown here as blue. And it's like this was, 2017. So like the methods were even slower than they are now. But the point is that it like gets to a much higher asymptotic value than model-based RL are kind of stagnant. So learn something, it's not that good. But if you start model-free training from there, it does better. But it's just like kind of unsatisfying that model-based RL is doing so much worse than model-free RL. Yeah.
So how, in like the real world scenario, are you doing the replanning with the replanning not like a bottleneck?
That's a good question. I think you do it with in Anusha's setting. She did it for pretty short horizon, like just 5 steps. And they use like an off-board compute. And so that made it work, but it's going to be a problem, and we'll discuss a method to fix it. But yeah, basically, if you have to do anything with longer horizon or a bigger model, replanning is just going to be tools. So we have to figure out better ways to do it. Okay, but there's going to be a significant gap from model free RL. And what we want to do next is try to like kind of close that gap a little, right? Yeah. Mm-hmm. Yeah. Yeah, so like model-based RL kind of like this version of model-based RL kind of stagnates here. And if you initialize model free RL from here, it'll get better. But like this one didn't really get better. Okay, so the next version that we want to do is a method that closes the gap. And it's basically based on one of the things that you just said, which is search with random actions is a terrible way of doing search, right? And so we're going to try and design. We said we do random shooting, we fix some errors with pre-planning. We're going to next try to do a better method of search, right? So we're going to do a better method for planning, and that's going to try and close the gap. Yep. And so if you look at this, general loop, the issue is that you're searching for a needle in a haystack, right? You're just like trying to do random actions and trying to find like the thing that is best. You increase dimensionality, you increase horizon, you'll never find it. So you're just like, it's like wiggling a whip around trying to find something, right? And so that can be quite difficult. It's like, easy way to characterize it is very, like the number of samples that you need to take to actually find what you want is like exponentially large. And so the trouble with this random search method is that it's extremely high variance, which means it needs a ton of samples. And so Alexi's question of like this, is going to be too slow for any hard problem becomes a bottleneck, right? And so what we need is a better sampling method so that we can search through these high dimensional spaces better. So what is an idea for a better sampling method? Like how can we sample better? Yeah. Right. That's right. That's exactly it. So what we're going to do is exactly what Raymond just said, which is inform your sampling function with your reward function, right? So you're saying that things where you have higher reward are things that you sample more of, right? Which is, we were initially sampling this completely from the uniform distribution, or you keep sampling IID uniform. Every time you do it, you keep sampling from the uniform. What Raymond just suggested is you want to inform your sampling distribution with the reward function. And so if things are higher than reward, you want to sample around them, right? And so all we're going to do is we're going to try and iteratively upweight your sampling distribution around things that are higher returns. Right? And so that's all the idea of MPPI really is. If you read the paper, it's extremely confusing, but like that's all it is. It's just this. And there's like some optimal distribution, something. Don't quote me on this, but essentially Raymond's idea is all that you do, right? You just say, let's sample a bunch of stuff. Let's upweight the sampling distribution around things that have higher returns, and let's repeat. And so essentially what this will do is it says, okay, initially you sampled a bunch of random trajectories this way. You found that these things have higher return, right? And so the next time you sample, you want to sample closer to these things. Right? So you no longer want to sample uniformly, you want to sample from a more informed distribution. Right? And so initially, so unlike random shooting where you just want to sample a bunch of things, choose the best one to execute, you're going to go through this iterative loop. You're going to sample a bunch of things, evaluate reward, take the things that have high reward, reweight your sampling distribution around them, sample some more, repeat, and then you execute.
Seems like we would like have a high, like the other like missing some of the things. Like see the sample in the beginning and don't find any good trajectory.
Yeah.
We're still gonna outweight the best one we found.
That is true. That is true. So that's just like an exploration problem. And there's no fixing that here. I think So we'll cover exploration in 2 weeks. There's like techniques you can use like optimism and like trying to get coverage to get like that kind of search to work, right? Which is better than just random actions. This method doesn't do that. So you can combine this method with optimism. And what optimism does is says things that are unseen, try to sample more, right? And that like helps you spread out in your state space more. This method doesn't deal with exploration. So it's going to get stuck in local optimism, just like this.
This is like the testing the function.
No, the transition function remains the same. Just your sampling distribution. And so let's see. In this procedure here, right? What you're going to do is you're going to sample this guy from uniform, this guy from uniform, this guy from uniform, right? And now what you're doing is instead of sampling it from uniform, you're going to sample it from some informed distribution, right? And so you're going to like sample a bunch of uniform stuff, upweight it, then sample from better distribution, upweight it, and then you're like, you just like iteratively improve your sampling distribution. So this procedure is done. But that's basically it. Okay, so the procedure looks as follows. You sample n action sequences, right? And then you say, you run these action sequences forward through your model. So as what you were saying, you freeze your p theta, and you're not changing your p theta hat. Right? You don't have any new data to make your model better. You're just going to run all of these sequences forward through p theta hat. It'll give you new s hats. Right? And you evaluate those s hats with your reward. And you upweight things that are higher reward and low downweight things that are lower reward. Right? So if you had your initial action distribution sample from pH, you're going to upweight those by exponential in sum of rewards, and that's going to upweight high reward things and downweight lower reward things. Right? And so you can update your pH to a better pH, and then you go back and sample again. And so the way that this is going to play in terms of like our overall procedure is that at any single time step, I'm going to like execute this loop many times. So at any time step, I'm going to sample a bunch of action sequences, run them forward through the model, refine my sampling distribution, repeat a bunch of times, then I'll choose my best first action, and then I'll play, and then I'll repeat this procedure. Right? So it's even more expensive, but it works a lot better in higher dimensional problems, right? And so the idea is you just like this is the important part, right? You're just like reweighting your sampling distribution to be closer to high reward. Right? And so all of this, remember, happens at a single time step of plan. Yeah.
Each action is updated by the entire batch screen.
Yeah. Because you need to like, you can't just take rewards as independent. So it's kind of like, you can almost think of this as policy gradient, but it's saying that like, take action sequences that are good, upweight them, action sequences that are bad, and downweight them. But all you're using this for is updating your sampling distribution, and then you're just going to do the rest. So unlike policy gradient, you don't care about policy parameters here, you just care about the best action. Yeah. And so you're just going to repeat this procedure a bunch of times. And this is going to give you what you call as MPPI, or model predicted path integral. And essentially it has lower variance, is a lot more efficient, deals better with high dimensional spaces, with the caveat that it doesn't do exploration. And it still has many of these like exploration problems that you have in most of our but it's a lot better than random shooting, right? And so you should definitely do this. This from Byron's group, it's excellent work. You should read the paper, but now that you know the simple version, go read the complex version. It's good. Okay, good. So essentially our recipe now looks like collect some data, learn your model, same as usual. But now you do planning with this MPPI plus model predictive control scheme, where you run this procedure multiple times within a single time step, right? And then you repeat, right? And so you're saying the only change from the last thing was that you're going to upweight your sampling distribution and like keep resampling these actions from the upweight distribution. And that's basically the only change. That'll make it a lot better. So the goal here is, or the point here is that it's better than random shooting because it has lower variance. And what Byron's paper tries to do is essentially derive this as like an optimal sampling distribution. But the nice part is a lot of Byron's results are basically with MPPI. And so this is with like a rally car that they had at Georgia Tech, where they like manually drove the car around with the remote control for forget exactly how many trials, but they're able to go like extremely fast with a neural net controller, MLP, 2 layers, and they're just using MPPI as their planning method. So to Alexi's point, like it's going fast enough to do real-time control in this setting. And so I think for small enough neural nets, it's fine. For other things, we have to rethink how to do it.
Do they have the any on board?
No, off board, I think, yeah. I think it's in that like chat there. I think you should go check the paper, but I think that is off board. This was like several years ago, so I don't think the Jetsons were as good. But I think now you can run a lot of these things on the NVIDIA Jetsons and they're good. Okay, so that is version 2, or version 1. We went to random shooting plus FPC. We made a better sampling. Right? So what we're going to think about next is we've kind of like talked about planning a bunch and how to make planning better, but we haven't talked about modeling much, right? So we haven't talked about like what is the issue with learning a model, right? And I kind of revealed the issues already, but the issue with learning a model is the same as the issue with behavior cloning, which means that like rollouts under your learned model may not be equal to rollouts under your true model, right? And so if you learn a model, this is your true rollout. And if you have a predicted rollout, it can look significantly different, right? So again, the issue is autoregressive generation, right? So by autoregressive generation, I mean like, if you guys did the homework, it's like when you generate and feed back into your model, right? So the way that model-based RL is going to work is you have S and A. It's going to give you an S hat prime. And then you have A prime. And this goes through your model, B theta hat to give you S hat prime, right? And as you go further and further, each of these has to go back into the model, right? So if you have a model that takes in S and A, let's say you made a little mistake at the first step, right? So you made a little mistake, like you made a little mistake getting here. And now you fed in an out of distribution state into your model. So you've like fed in something out of distribution, which means that your S prime prediction is going to be kind of wrong, right? And if your S prime prediction is kind of wrong, when you feed it back in, it's more out of distribution, which means your next prediction is going to be kind of wrong, right? And so you have this issue of compounding error whenever you have autoregression, because you're like, you've trained it for one step, and then you've asked it to do multi-step, but it's never seen multi-step, so it has no reason to be good, right? And so we've taken this like one-step training objective, and we've tried to roll it out multi-step, and this issue is going to like make the errors blow up as you go longer and longer and longer horizon. So if you just train a model, go home and try training a model, you see like it'll blow up in 5 steps or 10 steps. And so this is what makes model-based RL hard. It's this issue called model bias or compounding errors. It's just like when you feed things back into the model, little errors will become bigger and bigger and bigger over time. And so this happens because of lack of data, right? As in, if you made a little, like the errors will go down the more data you have and the bigger model you have, and you like, even if you got a distribution, you will cover that space, right? And so the thing is basically what I said. If you make little errors in state, you'll go to some OOD states. The OOD states unseen by the model will generate garbage, right? And the problem with generating garbage, so in behavior cloning, we were executing the real world, right? There was no model. We were executing the real world. You made an error, your policy gets worse and worse and worse and worse. But in a model, what will happen is that you will hallucinate something that the model thinks is true, but it's not actually true. Right? And so what can happen then is that it's arguably more dangerous, and that it like starts predicting things that are just like not true. And if they're not true, then you can execute really dangerous actions, but the model thinks that they're good actions, right? Yeah.
Wouldn't like having MPC with like replanning very often fix that, because like the true rollout and the rollout of the model like similar at first.
Yeah, so like it's daggerish, right? Like in a way, as in like you collect some more data, you retrain your model, wouldn't it fix
Get a
it?
snapshot of where you're
Yeah.
actually at and replan that.
Yeah, it's a bit like whack-a-mole in the sense like you like, okay, you deviated here and you collected some data. Okay, now this thing is good. Now I'll make it. And it's like you will like, unless you have a lot of data, you keep making these whack-a-mole type of errors. And so you might need a better solution in the long run. But that's a good point. And so most deep models can only roll out for 5 to 10 steps maximum, at least the vanilla ones. There's better ones in the like last 3 years that can roll out hundreds of steps, but they use like fancier architectures and fancier sampling. Right? But the problem is essentially just like in behavior cloning, we trained on the expert and then we deployed under the policy. It's like training doesn't match test, right? It's the same thing. It's like you train for one step, you're rolling it out multi-step. So training doesn't match test. That's the main issue. Okay, so if we wanted to fix it, how do we fix it? Well, one way of doing it is to say, let's change the training objective, right? Let's say that if we want to optimize for multi-step, then let's train for multi-step, right? And so one thing you can do is that this is a normal maximum likelihood error, which is saying that you try to minimize one step prediction error, try to maximize likelihood for one step prediction. You can, and this is often what you call equation error, right? So one step error. You can also optimize this thing you'll call simulation error. And what simulation error says is that you optimize your model, not just for one step, but for multi-step, right? Which means that you optimize the data such that when you like roll out through your data, it matches your states in like multiple time steps, right? And so essentially you can say that like you will have b theta, you'll stick in s and a into it, you'll get an s hat, and then you'll stick it back in through your model with the next a, and you'll get s hat whatever prime, and you'll stick things back in, right? So if you like think of the computation graph, it kind of looks like you have b theta, s and a gives you s hat prime. Now s hat prime and a prime go back into your model, b theta, give you s hat prime prime. This and this go back into your model, give you s hat prime prime prime, right? And so you can like repeatedly stick things through your model and then supervise the error across all, summed up across all of the time steps. So you can say the error is going to compare, the error is going to compare these two things. Sorry, 1 sec. The error is going to compare these two things plus, or sorry, this is going to be s prime, and this is going to be s prime prime, and compare it with s prime prime, right? And so you're just going to like take the differences and sum them up over all of the time steps. And so it tries to match it at multi-step.
What is that A prime?
Oh, it's a series of actions that you had in your days. Right?
The S hat prime and the A hat doesn't come from the same, right?
So it's saying that like, imagine that you had like, this is your trajectory, right? And this was like S naught, S1, S2, blah, blah, blah. You'll have like A naught, A1, A2, right?
Yeah.
And so you're just saying like, this is going to be this. And then you're going to try and match it to S1 when you stick in A1 over here. So you're saying that if you executed the training actions, you should get the training states. Right? So it is going to be wrong, but the whole point is that you really want the multi-step rollout of the same actions to match the states of training. And so it's saying that stick in all of the actions at training time, not different actions. And for those actions, it should match the training time in multi-step. Right? And so the whole point here is that you're not going to do one step loss. You're going to do like a multi-step loss, right? So you're going to just, yeah.
The same thing for behavior cloning.
No, you could not have because you didn't know the model. Right? In behavior cloning, you only have access to state action pairs from the expert. So here what we're doing is we're trying to learn a model which matches it in multi-step, right? In behavior cloning, you don't know the dynamics model. And so that's what makes it hard to do. Right? Yeah.
I like the auto regressive method where we do the forward pass with the predicted stage, but we do the top drop.
It's very similar. The difference is that what you did in homework was you did it in the behavior cloning setting, so you did it along dimensions of actions. Here you're doing it across time steps, but it's very similar.
Could you use like an RNN to execute?
You could do an RNN. What you do in practice, you do an RNN.
Anyone, do you see anyone from the real?
Yes. That's exactly what it is. You just use the you use the action sequences from the training data.
But what happens if like student?
This is student forcing, right? Or teacher forcing.
Okay,
But like this is the whole point, right? It's just saying that like what teacher forcing says is that when you like execute multi-step by feeding things back in, try to make it match, right? This is just like feature process. Especially if you use an RNN, it's literally. Right? It's like the same procedure. So yeah, it's the same. Right, so the point here is that you like, instead of trying to just match the first time step, like you do in like this objective, you try to match like multiple time steps, right? And so this is what we call simulation error, because you're trying to match not just the equation at one time step, but you're trying to like simulate through your model and make sure that your model is able to simulate multi-steps in the future, right? And so that at least training matches tests for whatever case steps you train on. But what makes this, why might this not work? Or is this the solution? Okay, I'll give you a hint. It's basically, it's going to be an unsatisfying answer. But it's basically because it's like often very hard to optimize. It becomes like a horribly non-convex objective if you're like sticking things back into the model. And it's just like becomes like often you'll find that the training loss doesn't even go down, these kinds of models. And so, especially with the neural net, optimizing these types of objectives is hard. At least I found it to be hard, and many people have. And so optimizing that is supervised learning. Optimizing that is not supervised learning, right? And so it's like more tricky. So it's like a challenging non-convex optimization. Most neural net things are non-convex, but this is more non-convex than other non-convex things. And this one is a lot easier to do. And so this might fix your problems, but you won't find it all. And so it's not that useful. And so most people in practice don't do an objective like that. Sometimes they do it with the RNNs, but that's hard to get to work. So we want to find a different solution to deal with compounding error. So we want to retain our simple model learning objective. We want to keep our simple model learning objective, but we want to like avoid these compounding errors, right? And model hallucinations and so on. So how can we deal with that? What's a different solution? So maybe useful thing for us to think about is like why are these models hallucinating in the first place, right? Like they're hallucinating because you're going out of distribution and you're going to things where you don't have data, right? So how can I deal with like, not considering this?
Make it like variational. So
Exactly. Right? So make it aware of uncertainty, right? And so you just want to estimate when you're out of distribution, right? When you don't have data, and then account for it, right? So like Varun was saying, basically you want to measure uncertainty, and that's what variational stuff will do. And you want to penalize for uncertainty. So if you're going to places where you don't have data, you're going to hallucinate some crazy stuff. And so like push those things down. And so a class of methods that deal with these compounding error problems are like, if you have maximum likelihood models, they look like this, right? You have a point estimate of your model, like your model is a point, right? It's going to give you some samples in the future. Those samples might deviate from the truth. But what you want to do instead is you want to have uncertainty aware models that are aware when they're out of distribution, right? And so if you have something that is aware of its uncertainty, then you know that that thing is out of distribution. If you know something's out of distribution, you can penalize for it. And so what you want to do when you're learning these models is not just get a point estimate, but try to measure and capture uncertainty. And that uncertainty is going to be something you penalize during planning, right? And so the point here is that hallucination is because lack of data correlates with uncertainty. If you measure uncertainty, you can deal with hallucination. Yep. And so what our goal is going to be is to figure out how to learn uncertainty aware models, use those uncertainty aware models to penalize model hallucination or account for this kind of compounding error. Okay? And so, okay, before I tell you how to do it, any ideas on how we measure uncertainty? Yeah.
It's part of your neural network model. But
Yeah. So I think we want to be careful about what type of uncertainty we think about, right? And so there's two types of uncertainty. One which is aleatoric uncertainty, which is like what you're talking about. Like if you have a stochastic environment, right? You're saying that like the stochastic environment can go here or here, and my model output wants to capture both of them, right? And so, that was bigger. Like, imagine that you had like a data, like a point where there's like a lot of variance, right? So imagine like, look at this point, look at how much variance there is here. Which means that your model output, like your true system has a lot of variance in it, right? Which means that there's uncertainty because like at that point, there's many possible outcomes. And so that's what you call aleatoric uncertainty, which is like essentially stochasticity in your environment. There's a different type of uncertainty, which is epistemic uncertainty, which comes from your lack of data, right? So if I don't have data, imagine that I like had data, you know, here, and I had data here, but I really didn't have data here, right? Like what'll happen then is that I like kind of don't know what happens in between. And if I don't know what happens in between, then I have uncertainty there because of lack of data, right? And so, to your point, like I say, I think we want to capture for hallucination, like our models are able to capture aleatoric uncertainty, but they struggle with capturing this epistemic uncertainty, and epistemic uncertainty is what's going to propagate and make these models hallucinate, right? And so what we want to do is capture this epistemic uncertainty that comes from lack of data, right? And so we don't want to capture like we already have methods to capture variance because we like talked about these diffusion models and energy-based models and auto-regressive models that all of them capture variance, but we want to capture like lack of data. Right? And so we want to get that, and that's going to allow us to control for model hallucination. Okay, so if we want to capture epistemic uncertainty, how do we do it? Right. Yes.
With variance spread.
That's exactly right. That's an easy way to do it. The Pavel's suggestion is basically run dropout, which means you drop out random like neurons from the neural net, run it forward k different times, and look at the spread of outputs, right? And if you've seen the data a lot, then you have low variance. If you've not seen the data a lot, you'll have high variance, right?
This paper on like deep probability estimation that takes care of this. I forget how they did it, but I know it was some kind of binning.
Okay, you should send it to the class. I think that'll be good. Yeah, no, send it to the class. There's like it's a huge space of literature. I'm not going to cover all of it, but that seems like a great one. And you should send your paper to the class. That'd be great. Okay. So essentially, what we're going to think about is essentially trying to estimate this quantity, right, which is like what is the distribution over policy parameters or model parameters given a data set, right? So normally maximum likelihood tries to estimate a point, like a point estimate. So for instance, if you look at any of our maximum likelihood objectives, this is like a point estimate. It's trying to find the best data, the single point, right? Which doesn't capture uncertainty. And so what we're going to try and do is we are going to try and measure this posterior. So we're going to try and measure what is the space of models that are consistent with the data according to some prior, right? So if you're familiar with Bayesian statistics, right, we have P of theta, which is our prior, P of D given theta, which is our likelihood, and we want to estimate the posterior, which is P of theta given D, right? And P of theta given D, you can think of it intuitively as D is your data, so it's going to be S, A, S prime, whatever. Right? And theta is going to be the set of model parameters that are consistent with that data. And so going back to our figure, what it's going to let us do is it's going to say, okay, we have like a bunch of models that are consistent. We can have like a different model that is consistent and a different model that is consistent and a different model that is consistent. And all of those are consistent with the data, but you want to maintain like a spread of models which are consistent with the data. And if you have the spread of models, then you know, you can look at the like difference in the model predictions to know when you have data versus you don't have data. And so if you know how to estimate the posterior, you can tell which places don't have data and which places do have data. And so the point is you want to estimate what are the, like, rather than estimating one model, you want to estimate like a set of models or a distribution over models that are consistent with the data, right? And that's what a posterior is going to be, at least approximately. And so P of theta given D is just like the distribution over consistent models. And if you use Bayes' rule, you can write the posterior this way, right? And so this is just Bayes' rule. It's just saying the likelihood times the prior by the partition function, right? The likelihood here is going to be your like maximum likelihood objective, right? There's going to be like MSE or anything from maximum likelihood. It's going to be log P S prime given SA. The prior is just going to be some prior over policy parameters, right? And then you need to estimate this posterior. If you estimated this posterior, it gives you a measure of like uncertainty, right? Does that make sense? So you have like, this is going to be your likelihood. So it's going to tell you how consistent is a model with the data. This is going to be a prior over all possible models. And this is going to give you a posterior over what is the distribution of consistent models. Now, so this is just base rule. Now, what makes this hard to compute? And this seems like easy enough. The bottom thing, right? You have to integrate over all models. That's a pain in the ass. So we want to avoid that. Especially now theta is a set of all policy parameters. So it's like a disastrous space. And so I don't think you can. Yeah, you can, but then you don't get uncertain. And so there's, oh, I thought this was going to go away. Okay, I guess we're stuck with these words for now. But essentially, all of these methods here, like Bayesian neural net, ensemble method, are just approximations to your Bayesian posterior, right? The posterior is going to help you measure uncertainty, the uncertainty will help you penalize planning. And the difficult part is this partition at the bottom, which makes it hard to estimate. And you can have lots of different approximations that kind of get you to get an approximate data, right? And so I'm going to skip the Bayesian neural nets because it's going to be too complicated. But let's think about the easy one that's more practical, right? Which is just like learning an ensemble of models. Like Pavel was saying, it's like dropout. Essentially, if you have an ensemble of models, they will agree on data that you have and they will disagree on data that you haven't seen, right? So imagine that you had like some data here and some data here. So you had some data here, some data here. You'll have a bunch of models that can agree on that data and like disagree elsewhere, right? And so your like curve will look like this when you have when you train an ensemble of models. That means you have like k different models that often you can even train on the same data just with different initializations. You'll find that in areas that have data, they'll agree because they're all trained on that data. But in areas that you don't have data, because they're like initialized differently, you'll find they have like high variance. And so there's often a really effective, simple method for uncertainty estimation, which lets you estimate variance of the ensemble as a proxy for Bayesian uncertainty. And it's like, oh, but the point here is that you just train a bunch of models, look at how different their outputs are, and that gives you a measure of uncertainty. So things with high variance are high uncertainty, low variance is low uncertainty. That's it. Right. So here what we would do is we train a bunch of like dynamics models, like learn like k of them, right? And then just look at the difference in predictions. And predictions are high variance. Hallucination, it's low variance, it's not hallucination. Yeah.
In practice, how large of a case? It's
Like 5 or so. So it can get bad with the huge neural nets, which is why the dropout suggestion that Pavel had is easier because you can just like drop out neurons within the same network and it has the same. Exactly. So there's this researcher Pavel Ismailov at NYU who has a bunch of really cool work connecting these two. So you guys should look at that. Okay, so this gives an approximate posterior, and essentially what we're going to do then is rather than learning one model, you learn an ensemble of models. If you're being proper about this, you would train this on different subsets of this data sample IID. But often what you do is use the same data and you just like differently initialize and it still does pretty well, right? And then once you have that, we will then integrate this into planning, but we will do that next week. Cool. And discussions on Thursday will be fun. Thank you.